Swayam Prabha. Digital India. Educated India.
So far we have been talking about Langevin equation in the context of Brownian motion and various kinds of Brownian motion, and also applying Langevin equation for chemical kinetics. In discussing these framework, we looked at some analytical way of answering these problems, but the true power of Langevin equation lies in modeling a more complex phenomena, a more complex process for which there is no direct analytical solution. So one will have to look at numerical methods. So in this class I will be talking about some simple Euler-like numerical method applying for Langevin for Brownian particle as well as for chemical kinetics with some test cases. So the first example I want to talk about is a very simple Brownian particle, a free Brownian particle in 1D. We do this because we know analytical solution for this. When we construct a numerical algorithm, we can test the numerical accuracy, numerical prediction with the analytical results. So for this case, we will take the overdamped limit So what I mean by overdamped limit is that the initial terms are neglected, and this can be neglected for time t much greater than the initial time, which is defined as m by gamma. Okay, so then the particle has an overdamped behavior, and we showed in one of the previous classes that the dynamics of this particle is governed by dx by dt is equal to 2d eta of t. Okay, so we are now only looking at how the position of a Brownian particle in one dimension changes through this random noise. This d here is the diffusion coefficient. Now what we want to do is we want to construct a very simple numerical technique for solving this numerically in a computer, and before we do that we can think of non-dimensionalizing this equation so that all the parameter can be kept as some sort of groups of non-dimensional numbers. Okay, so here we have this x, which is a length scale, and what's the natural length scale in this problem? If you have to choose a length scale for this problem, what would that be? I want to non-dimensionalize x, so I need a length scale. What can that be? Micrometer? Anything that is yes. So any length scale, diameter of the particle or the radius of the particle can be taken as a length scale, because that's the only length scale that is there in the problem. Okay, so we will take r, that is the radius of the particle. We will take this as the unit of length. So therefore we can define a non-dimensional x position of the Brownian particle as x by r. Okay, so we are trying to cast this equation in a non-dimensional form, so we need to have a basis unit for length, time, and so on. So we have time here. What about time? How can we think about a time scale for this problem? Related to, you mean this initial time? This initial time we don't want to be, so we want to be much larger than this, so this is not relevant for the time scale in our problem. What else can be defined as a time scale for the problem? You have something? R square by d, yes, exactly. So we can think of this group r square by d in the units of length. This will be in meter square. This is in meter square by second. So basically this comes in time unit. So we can think of this as a scale for time. So we will have so we call this as tau d, which is called the diffusion time. Okay, time scale related to diffusion. So non-dimensional time is here, and this random force, this will have the units of 1 by time. Actually 1 by square root of time, because this correlation of this autocorrelation of this function is a delta function, so that will have 1 by time. This will have 1 by square root of time. So this has to be also non-dimensionalized. So the way you would do that is eta into square root of tau d, that is so now we can actually substitute all these non-dimensional numbers here and then convert this equation. So this non-dimensional equation, once we choose the length scale and time scale, this will become a non-dimensional equation like this. You can see diameter, radius, all that physical parameters are gone, because we are casting this into some sort of a non-dimensional scale. Okay, this is applicable for a very large Brownian particle or a very small Brownian particle in a viscous liquid or less viscous liquid. All that is mapped out here. Okay, all the dimensionality, the fluid property are all sucked into these non-dimensional quantities. Okay, so now we want to basically solve this particular equation numerically. Now when we try to non-dimensionalize this, what we will do is we will try to write this in a discretized form. So this is a differential equation, and we try to take a small delta t. Okay, over that delta t we try to discretize this equation. So dx becomes delta x, dt becomes delta t. Okay, now if you look at this particular quantity, this eta star here, this is a normal random variable with mean equal to 0 and variance is equal to 1 by delta t star. Or we can simply write this as 1 by square root of delta t, a normal random variable with 0 mean and 1 unit variance. In the very beginning of the course, we already know how to generate a Gaussian normal random variable with a 0 mean and unit variance. So we can call that function to generate this number and take that number and divide by the delta t delta t star, then you would have actually created this random component. Okay, so this equation then can be written as delta x star is 2 So between two subsequent time interval, the exposition changes, the non-dimensional exposition changes by this amount. Okay, you are going to call a random number, normally distributed random number in the 0 mean and 1 unit variance, and then you multiply by this square root of 2 delta t. That is the jump this Brownian particle is going to make between subsequent time steps. So if you want to write a small computer code for executing this, you would probably follow this kind of an algorithm. So first we will do an initialization, that is that x star at time t equal to 0. Okay, you can start from the origin, and you may want to choose that in the trajectory you are creating in discrete time steps. So you want to decide how many number of data points you want to create. So you say that I want n step number of data points. This is something that you have to choose, 1000 points, 10,000 points, and so on. So, and then you also decide the total time of the trajectory. So just like how we use Runge-Kutta method or Euler method to solve deterministic ODE problem, where you say how many time unit you want to solve and what is the step size you want to choose and what is the number of steps. They are all very similar to that. Okay, so once you have the total time you want and the number of data points in that time, you can choose your delta t star as t by n step. Okay, either you choose t and n step and then decide delta t star, or else you determine what delta t star you want, how small you want, and the total time you fix, and then accordingly you can choose n step also. Okay, they are related by this way. Now in the second step, you basically run a for loop for I is equal to 1 to n step. Okay, and then you say that you first generate a normal random variable with a 0 mean and unit variance. Okay, inside the for loop you create one of this, and then you will update based on this propagation. You are going to write x of I is equal to x of I minus 1, that is the previous step, plus square root of 2 delta t star n of 0 comma 1. Okay, so when I is equal to 1, you will use the initial position that is mentioned here. When I is equal to 2, you will write x2 is equal to x1, the previous position, plus this term is the delta x, the increment in the x position, and this loop will be executed n step, and at the end of the for loop you can print x versus t. Okay, and then you basically you have generated a trajectory of a Brownian particle. This algorithm creates one trajectory, but generally for getting statistical properties you may have to probably generate hundreds and thousands of trajectories so that you can average over the ensemble average to calculate mean square displacement and so on. Okay, so you will have another loop above this to create this trajectory over and over, maybe 100 times or 200 times. Okay, so this is a kind of a pseudo code. It's very easy to code this in MATLAB or Python or whatever. Okay, it's very simple. Yeah. Okay, the star. Yeah. Yeah. Thanks for pointing it out. Yeah. So step 3 is either you print it or you plot x versus t. And what is t? T is nothing but I times delta t. So inside this loop, when you go to I 1 to n, you can update your time I times delta t. Okay, so therefore you would have created a data for every given time a corresponding position. Okay, again we are all doing it in non-dimensional units. If you look at this particular algorithm, the displacement that we have here, it does not depend on the current position. So it depends only on this delta t star. Okay, so remember when I was talking about Langevin equation, I was talking about a time scale. It shouldn't be too small, it can't be too high. If it is too large, then the propensity function may depend on the current state. Okay, and if it is too small, you may not have enough events to justify the the assumption that we made. Okay, but in this particular special case, you don't have to really worry about how small, how big the delta t should be, because the choosing of this delta t does not affect the current state. The propensity function does not change. So you have a choice to make delta t as big as possible. But generally you want enough points over a trajectory point. So delta t does not impose any constraint in this particular problem. But I'm going to talk about another problem where this increment will also depends on the current position. Okay, and then you cannot make this delta t too large. Okay, so that brings me to the second problem. The second problem is a Brownian particle in harmonic potential. We already discussed this problem in the context of optical tweezers, where a Brownian particle is confined to an harmonic one-dimensional harmonic potential, and then in the overdamped limit, we have dx by dt plus k by gamma x, that is equal to square root of 2 d eta t. So this is the additional term that comes because of the harmonic potential, which is kind of confining the particle within the potential well. So this is also dimensional, just like how we did in the previous case. You can try to convert this into a non-dimensional form. When you do that, this factor, spring constant by the drag coefficient, this will come out as another time constant. Okay, so so that there's going to be a parameter for this. In this case, there is no any other parameter here, but here this term will bring a characteristic parameter to this problem. So I will give the equation, the final equation directly here. After non-dimensionalization, you will see that delta x star is minus f So we take this equation, apply non-dimensionalization, write it in a discretized form. This is what you will get. Here you can see there is a parameter f that is coming up, and this is defined as I said before, it is a non-dimensional parameter defined as kappa or k over gamma times square root of r square by d. Okay, so this is a non-dimensional parameter that tells you how stiff the spring is or how stiff the potential is confining the particle. Okay, this is basically entering as a parameter. And if you want to write this in terms of normal random variable, we can write this as okay. So this is going to be our displacement over delta t. So compared to the previous case, in this case when you try to initialize, you also have to choose this parameter f that tells you about the strength of the potential that is confining the particle. So with this you would calculate what this delta T star is. This is step 1. Then you run a for loop. So generate a normal random variable. Then I apply this increment. So xi is equal to xi minus 1 plus, or rather minus, f So this is what I was trying to say, that if you look at this particular incremental formula, we have this additional term compared to the previous case. The accuracy of this term will be determined by how small or how big this delta T is, because when I try to take the differentiation of this, we have assumed that over a period of delta T this x remains almost same, but this may be violated if delta T is too big. Okay, so in this problem, how small or how big the delta T you choose will affect the accuracy of this trajectory. The smaller the better, because when you have a small delta T, it's very likely that the x will not be too different from the previous case. Okay, so this is an explicit method. Whatever you need to update, everything is known on the right hand side. Okay. So in this case, I have added extra step. You can also add this step there to increment your time, and then once you come out of the for loop, you would have generated n step number of positions, and you can plot and print the x versus t, and this again creates one trajectory. Again you have another loop over this to generate as many trajectory you want, and then you do some sort of statistical averaging. Now I have two more examples, but these two examples coming from chemical kinetics. Okay, so these two examples are for Brownian particle diffusion, and we will look at the chemical Langevin equation for chemical kinetics, and then look at how this algorithm works. In this simple example, we have a reversible reaction. The forward reaction is a zero order reaction. Okay, so this is some species which is giving rise to x. The forward rate we consider as a zero order reaction, whereas this x can also decompose into phi, and that we consider as a first order reaction. Okay, so now for this case, how are we going to set up the Langevin equation, and how are we going to numerically integrate that is the context here. In this case, the state variable is basically the number of molecules of x. Okay, so x of t, this would be the number of molecules of species x. Okay, so we are interested in the dynamic evolution of number of molecules of x through Langevin equation. So here we identified there are two reactions. Reaction R1, which is phi giving rise to X, and reaction R2, which is the reverse of this. Okay, so we have identified the reaction channels and the corresponding stoichiometry. So here the propensity function A1 is simply C1 because it is a zero order reaction, whereas in this case the propensity function A2 is C2 times X. In other words, in this case H is 1, in this case H is equal to X. So I want you to recollect that the way that we defined the propensity function is something like this. There is a rate constant and then there is a multiplicity factor. How many possible ways in which this reaction can happen? In the case of a zeroth order reaction, H is simply 1. The rate depends only on the rate constant. It does not depend on the amount of phi here. Whereas in the second reaction, it is rate constant times X. X is the number of molecules of X that is present at any time. So the propensity functions are written as this. Now in terms of the state change parameter, the state change variable, when this reaction happens, for the first reaction, for the first component, this is basically +1. In this case, if the reaction happens, this is going to be -1. So what we are saying is, whatever the chemical stoichiometry we have written here, we are trying to decode what this equation means. First we are saying how many possible species are present that we want to track. In this example, there is only one species I want to track, which is X. So I am defining a random variable X that refers to the number of molecules of species X. Okay, number of species is fixed. Next question is, how many reactions? There are two reactions. What are they? The forward reaction, phi giving rise to X. The other reaction is X giving rise to phi. These are two independent reactions, right? Now once we specify the reaction, we have to specify two additional things. How do we write the propensity function? In other words, the rate. Okay, and how this reaction will change my state variable X. Basically meaning that we have to define what is A and what is nu. A for the first reaction is simply C1 because it's the zeroth order reaction. And how this reaction is affecting my state variable X? It is increasing X by 1, so it's +1. When I go to the second reaction, my rate is given as C2 times X. C2 is the constant, rate constant. X is the number of ways in which this reaction can happen. That depends on how many number of X molecules are present at the time t. Okay, so the propensity function or the rate constant, the rate is C2 times X. Now what happens when this reaction happens? When this reaction happens, my X decreases by 1 because I am assuming they are all unimolecular reactions. So this now completes everything. Number of species is known, number of reactions are known, propensity function for the reactions are known, and the state weight change variable for the reactions are known. That basically completes my specification. One additional thing we have to say is the initial condition. Okay, in this case we can say we start with the X equal to 0. Okay, then the reaction will anyway continue. The phi will give some amount of X and X will react back. Okay, so we have to specify the initial condition also. Okay, so now we have completely specified the problem. So with this, we will go back to the chemical Langevin equation, the general form, and then rewrite this. So we wrote that for n number of species interacting via m number of reactions, this is a chemical Langevin equation written for each species I, where I goes from 1 to n. These summations are for all the reaction channels. Okay, so this is a general expression for n species reacting through m number of reactions. So now we know that there is only one species and there is only two reactions. Okay, and we know all the parameters that we need here. So let's write that dx by dt. I'm not putting any suffix 1 here because there's only one species. Here j will go from 1 to 2. Okay, so when j equal to 1, a1 is c1 and nu 11 is anyway plus 1, and when j equal to 2, we have minus 1 c2x. So when I expand this term, you will get c1 minus c2x. When j equal to 1, a1 is c, right, and this is plus 1, so you get only c1. When j equal to 2, this a2 is c2x and nu is minus 1. Okay, so then what we can do is the second term, which would be square root of c1 gamma 1 minus square root of c2 x gamma 2, isn't it? So now writing this in discretized form, we write delta x I have put here n1 and n2 because this n1 is for the first reaction and n2 for the second reaction. Basically, they are pair of normal random variables with the 0 and 1 mean and variance respectively. So what you are doing here is that you look at the reaction chemistry and then look at the propensity function and the state change function and everything, and then you take the general chemical Langevin equation, substitute how many species are there and how many reactions are there. In this simple example, there's only one species, but there are two reactions, and then you get this, and then you write this into a simple Eulerian form, discretized form, and this is the one that tells you between time delta t how X is changing. Okay, so then you can write an algorithm, initialize it, specify the rate constant C1, C2, choose your time, how much you want to simulate this problem, number of steps you choose, accordingly delta t is chosen, and then you run a for loop from step 1 to n step, and then you're going to calculate two. If you want to add, you can actually have one statement here saying that generate two normal random variables, because there are two reactions, you need two of them, and that one will be used here, another one will be used here, and then get the displacement or the change in the delta x, and that is added up here, update the time, and this loop will go on till n step, then you can print the trajectory. Again, this is one trajectory of a chemical kinetics. You can actually automate for any number of trajectory you want. And one important thing you have to realize here is, I am not using the I for the species identity, it is for the time. This is I at the time, I minus 1 time. Okay. Now let us take little more complex reaction, the Michaelis-Menten reaction, which involves more species and more reactions than this. No, I'm sorry. This is not implicit. Yeah, this should be x minus 1. Yeah. So this also is an explicit method. Yeah, please correct that. So the fourth problem is Michaelis-Menten. Michaelis. So the way to think about this set of reaction is that you have some sort of an enzyme. Okay, so this enzyme reacts with the reactant or a substrate. Okay, so the way it happens is, first the enzyme combines with the substrate and forms a complex. Okay, and this complex further decomposes into the enzyme plus some product. So enzyme here acts as a catalyst. Every one enzyme combines with one substrate, gives a complex. That complex decomposes into an enzyme back, so this enzyme can come back to this reaction again, and then effectively one substrate is converted into one product X. In addition to this, if you look at this problem, enzyme is conserved but substrate is consumed, so this reaction will come to a stop at some point of time. But if you top up this source externally, you add with certain rate, so the source gets replenished. So this is a Michaelis-Menten reaction network with substrate input. Okay, so substrate is constantly provided in the system. That substrate is consumed by this enzyme to produce X. Okay, so that is the reaction network. So what are the things we have to initialize for this to happen? What should be non-zero to initialize this reaction? Should enzyme be non-zero? We need enzyme, right? Without enzyme, this reaction cannot happen. Substrate, we can start with a 0 also, because we have this source. So substrate can be 0, but this source is going to keep on adding to it, but enzyme has to be non-zero. This can be 0, this can be 0. Okay, so you can see what is the minimum requirement for initiating the reaction network. Okay, that's one point. The second point is, how many species we have to track? Number of species. Do we have to track S, substrate? Yes? Yes, we need. E, we need. C and X. So basically there are 4 species. Yeah. Sorry? Phi is in some reservoir. You don't really account for how much is there. It's constantly putting some amount. You don't worry about where it's coming from. It's something that we don't want to account for. Okay? Because that is not limiting my reaction. So the quantities that we want to track are these 4 chemicals, or 4 species. And how many reactions? number of reactions. We have 4 reactions, right? 1, 2, 3, 4. Okay, so we got 4 reactions and 4 species. So we can identify, so maybe I'll make it in the tabular form. So one more thing I'm doing here is that these are chemical species. I want to represent their concentration as x1, x2, x3, x4, so it's easy to write. Otherwise, you have to write x, some sort of, you have to use a letter symbol. Okay, so yes, x1 means concentration of S, x2 means concentration of E, and so on. So okay, so now I have identified 4 reactions. These are the 4 reactions. Okay, for each of this reaction, I write the propensity function, assuming they are all elementary reactions. So this is a 0th order reaction. So A1 is just C4. This one becomes C1. This is denoted by x1. This is by x2. So you have C1 times x1 x2. And the reverse reaction is A3 is C2 times x3. And the last one is C3 times x3. Okay, propensity is done. Now we have to see when each of the reaction happens, how is the molecules of other species are changed, okay, whenever one reaction happens. So that we write into a vectorial form here. When the first reaction happens, it actually increases S by 1. It does not change any other population, 0, 0, 0. Okay, we have 4 elements here because we represent 4 species. If I look at the second reaction, S goes down by 1, E goes down by 1 by these 2, and C increases by 1. X is not affected. Here this is just opposite. So you can see the inversion of this problem, that in this reaction S is generated, E is generated, C is consumed, X is not affected. The last one, S does not enter here, so 0, E is generated, C is consumed, -1, and this should be 1. Okay, I think I made a mistake here. So X should be 1. Yeah. E generated, C consumed, X generated, and S is 0. So now with this information, we got 4 species, we got 4 reactions, and we have the propensity function, and we have the state change variable, and you have to basically apply this in the chemical Langevin equation, and then you will have a series of ODE for x1, for x2, for x3 and x4, and you will have to update the state change variable through some sort of an algorithm. Okay, I have given that in my notes, but you can also write on your own. Okay, so with that we'll stop.